So here in number 44, we have a rate law problem. The problem is about two reactants, A and B, being mixed together, forming compound C. And we are trying to figure out the order of the rate so that we can write the overall rate expression. This first part, we're figuring out the order with respect to reactant A. So in order to do this, we're going to look at our data table here, and we're going to figure out what two experiments we can use that have A changing but B staying the same. And so if we look at that, we see that here in experiment 1 and 2, A changes and B stays the same. So we're going to use experiment 1 and 2 for this one. 1 and 2. And then we're going to set up our equation. So if you remember from when we did these problems, we're going to look at how the rate changes. So the change in the rate is going to be equal to the change in the reactant that we're looking at, in this case A, raised to the x power. We're going to see what factor that changes by. So if we look here, we see that our rate goes from 4 to 8 times 10 to the negative 3. So if we wanted to know what factor that changed by, the easy way to do it is just to divide it. 8 times 10 to the negative 3 divided by 4.0 times 10 to the negative 3. And what we would get from that is 2. So the rate doubled. And then we're going to look at our reactant A. It went from 0.05 to 0.1. So that is also doubling. And then we're going to raise that to the x. So now we have to ask ourselves, 2 to what number, what power, equals 2? Well, in this case, x is going to equal 1. Because remember, any number raised to the first power is just equal to itself. So the order with respect to A is going to be first order, where x equals 1. So then if we scroll down to part B, we're going to see what is the order with respect to B. So now we have to look back up at our data, and this time we want to see where B changes, but A stays the same. So we can see that A stays the same in 1 and 3, and B changes. So we're going to use experiments 1 and 3 for figuring out the order with respect to B. And we're going to again look at the change in rate is equal to the change in B this time, the reactant that we're dealing with, raised to the x power. So again, we're going to look at how 1.6 times 10 to the negative 2 is related to 4 times 10 to the negative third. And what we find out is that when we do that division, that the change in rate is an increase by a factor of 4. And then we're going to look at our change in B. And we went from 0.05 to 0.1, so that's 2 to the x. So now we have to ask ourselves, what is the power that we can raise 2 in order to get 4? And that answer then is 2. 2 squared is 4. So x equals 2. And that means that it is second order with respect to B. So now we scroll down to the next question, what is the rate expression for this reaction? And remember, the general rate expression is always rate is equal to constant K times the first reactant raised to the x times the second reactant raised to the y. If there were a third reactant, there would be another one raised to the z, however many reactants you have. So for this particular reaction, it's going to be rate is equal to the K constant. A was first order, so you can write the 1, but you don't have to. You can leave it without the 1. And B was second order, so that's going to be raised to the second. Then the final question here is, what is the overall order of this reaction? Now the overall order is equal to the sum of the order of the reactants. So in this case, the overall order is going to be equal to 1 plus 2. And it's the sum of all of the orders of each of the reactants. And so in this case, the overall order is third order. And that's how you do these rate law problems.